Well, if weather permits, the picture will be taken right after Paolo's talk, who is our next speaker, Paolo Piccione from Universidad de Murcia, no, from USP, and he's going to talk about bifurcation of CMC Clifford tori in Euclidean spheres.
Okay, I think I get this on. All right, well, I'm very glad to be here and talking at this conference in honor of my friend Marcos. And since this will be a let's say, friendly talk, I decided that I should make my presentation visually more appealing. And for instance, I included pictures of my collaborators. And the result I will talk about has been done with Luis Alias and from Murcia. And if you don't know him, or if you don't remember what it looks like, that's him. Okay. Okay, and also I got this picture from Marcos from his webpage. So happy birthday! I'm very glad to be here. And then before I get into some more serious stuff, I wanted to share another thought with you, which is the following. If you look at the list of conference speakers, you will see that this list consists of two categories of people. One is the set of well-respected geometers, and there's another category which is Marcos friends. And this is me in the picture. Okay, this is the outline of my talk. I will discuss with you a problem of bifurcation of embeddings of tori into Euclidean spheres. And so there's a family of embeddings that are very well known. They are called the Clifford tori. So I will describe very shortly these objects to you. And then I will talk about the spectrum of the Jacobi operator of these embeddings, and I will give you the statement of our bifurcation result. And then I will talk about the proof of this result, how we got it, and describe more or less the variational framework of this problem. So I'll talk about bifurcation. I will give you an abstract equivariant bifurcation result that applies to our case. And then I will talk about the CMC variational problem with the functionals and the manifold of embeddings. And finally, I will tell you how one computes local homological invariance of these objects. And at the end, I will probably be able to also discuss another result, another bifurcation result with fixed boundary. Okay, so this is the plan of my talk. Let's see. Okay. That is a picture of Clifford that I found on Wikipedia, I guess. This guy's with beard. The family of CMC Clifford tori are embeddings. Okay, what you do is you choose two integers, j and m, j less than m, and then you take the torus Sj times Sm minus j, and you embed it into Sm plus 1 by doing this operation. Well, you fix a real number between 0 and 1, and then to the pair PQ, P is in Sj and Q is in Sm minus j, you associate the point r times P, comma, square root of 1 minus r squared times Q. Okay, that's one of the easiest embedding of the tori that you can think, of the torus that you can think in the sphere. And if you, it's an easy computation to see that this has constant mean curvature, which is given by this formula that involves m, j, and r. Okay? This is the mean curvature of this embedding. So in particular, if you solve a very easy quadratic equation here, set this equal to 0, you will find that for r equals square root of j over m, then you get a minimal object. That quantity is 0. Okay, that's called the That's the minimal Clifford torus. Actually, that was when most people talk about Clifford torus, what they mean is the minimal one, which is this one here. For instance, when J is equal to 1 and M is equal to 2, so you have an embedding of S1 times S1 into S3, then the minimal radius is 1 over square root of 2, right? Okay. Yeah. Oh, okay. You mean this?
It's easier to...
Yeah, you're right. It's that I have to control 3 things at the same thing, and that's kind of... okay, yeah. Let me tell you how things started. I was in Murcia with Luis once, and he showed me a computation that he had made a few years earlier with Aldir Brazil and Oscar Perdomo, if I'm not wrong. He showed me how the spectrum of the Jacobi operator of these embeddings is. That's an easy analysis that he had done with his friends. The Jacobi operator is a differential operator, is defined on, let's say, functions on the torus, which is given by, okay, this is the Laplacian of the Riemannian manifold given by the product of the spheres with the radius r and square root of 1 minus r squared. So this is a Laplacian of the product of 2 spheres. And then there is the operator of multiplication by the Ricci curvature, and then the operator of multiplication by the square norm of the second fundamental form. This is the second fundamental form, okay? Now what happens in this very special case is that the Ricci curvature of the ambient of the sphere is constant, 0.1. That is a very, very interesting fact. And second, also the norm of the second fundamental form is constant in this case. So the spectrum of this object is just the spectrum of this Laplacian up to a shift, right? Now also the Laplacian of the product of spheres is easy to analyze, because what you do is basically you just add eigenvalues of the Laplacian of this manifold and of the Laplacian of this manifold here. So an element is in the spectrum of the Laplacian of the product of 2 spheres if and only if it is given by the sum of an eigenvalue of the first sphere plus an eigenvalue of the Laplacian of the second sphere. And also the multiplicity is given by the sum of the multiplicities. And of course everybody knows the spectrum of spheres. So it consists, this is the spectrum of a sphere in dimension j of radius r. It consists of an increasing sequence of eigenvalues, I mean counted with multiplicity, given by some formulas, whatever. Also this one here, this is the Laplacian of the other sphere. That's another increasing sequence. So you have 0 in the spectrum of j if and only if you have the sum. This is an eigenvalue here. This is an eigenvalue here. Maybe I should do it this way, yeah. And this is that constant that comes from the Ricci curvature and the second fundamental form. So whenever you have this quantity equals 0, you have a 0 in the spectrum. In particular, if you take the sum of sigma 2 and rho 2 with this object, you always get 0, no matter what m and j are. And the multiplicity of this 0 is given by this number. And at some point at the very end of this conference, we'll get back to this number here. That's why that bottom back is there. No, okay. Then if you want to find the other zeros, you have to analyze all possible sums here. But if you use smartly the fact that this is an increasing sequence and that sigma 2 plus rho 2 gives you 0, you will find that zeros are only of the form sigma 1 plus rho L or something, or sigma I plus rho 1. So the analysis is easy, and you prove very easily that there exists 2 sequences, Ri and Sl. One goes to 0 and one goes to 1, with the property that the Morse index of the Clifford torus has a jump exactly at these values of the R. That is, The Morse index jumps whenever there is an eigenvalue passing through 0. Okay? So you make this, and this is a very explicit computation. There is absolutely nothing involved in this. Okay, so this is what Luis showed me. And I had worked earlier on a bifurcation problem, and everybody who works in variational bifurcation knows that whenever you have jump of the Morse index, that's a sign that you may have bifurcation. So I said, okay, then we have a bifurcation problem here for CMC embeddings. This is very natural. The constant mean curvature is a variational problem. Like if you have a compact manifold, let's say oriented, and you have a Riemannian manifold, N, in codimension 1, then an embedding, well, the mean curvature is the trace of the second fundamental form, and the variational principle is that the embedding has constant mean curvature if and only if it is a critical point for the function area restricted to fixed volume variations, okay? We'll discuss this principle in many details very shortly. So we have a variational problems, we have jump of the Morse index, and probably that means that we have bifurcation. That's the idea, right? Okay, but the thing is that having bifurcation means that you have a family of other embeddings, but there's a trivial way that you can produce other CMC embeddings out of a given one, and you can build, for instance, congruent embeddings. When are two embeddings congruent? Well, you say that x1 and x2 are congruent whenever you find a diffeomorphism of the source manifold, phi, and an isometry of the target manifold, n, in such a way that this diagram commutes. Okay? What that means is that x1 and x2 are congruent when they're the same thing up to changing the parametrization. Oops, I find this somewhat difficult. Having to deal with two fingers at the same time. So up to a change of parametrization and up to isometry of the ambient, they're the same things, okay? And of course, if you have a CMC embedding, any other embedding which is congruent to that one is also CMC. So when you talk about bifurcation, you want to make sure that the bifurcating branch is not done by something which is congruent to that. Otherwise, you don't really prove anything, right? So what that means is that you have to take into account the actions of two groups. One is the diffeomorphism group of the source manifold, and this acts by composition on the right. You see the phi here is on the right. And then you have the isometry group of the target manifold, which acts by composition on the left, okay? So when you may want to have a bifurcation result that keeps into consideration the action of these two groups, so you're going to have an equivariant bifurcation problem. How do you deal with these groups? Well, this diffeomorphism group is a huge, nasty object because it's an infinite dimensional Lie group, well, whatever that means. But the thing is that the action of this object is free. So that means that if you take the set of embeddings of M into N, you can mod out the action of this group because the action is free. On the other hand, the action on the left of the isometry group is not free. You can have two embeddings that when you are obtained. Well, now you can have an embedding that when you apply on the left an isometry of the ambient space, it remains equal to itself, right? So you have stabilizer, and you can't really mod out this group. But what you can do is, well, but the thing is that this group is now compact. It's a finite dimensional compact Lie group, so it's easier to handle. That's the thing. Okay. So let me tell you what we managed to prove. I have to read this. Okay, suppose you're given this family, you fix J and M, and you consider this as a family of CMC embedding depending on the parameter R. R is in 0, 1, okay? So you fix these objects, and the statement of the theorem is that there exist two sequences, one going to 1 and one going to 0, such that the corresponding CMC Clifford tori are accumulation of pairwise non-congruent CMC embeddings of the same manifold into Sn plus 1, and each of these, let's say, bifurcation branch of accumulation is not congruent to any member of the Clifford family, okay? Besides, for all other values of R that do not belong to these sequences, then the CMC Clifford family is stable in the sense that if you have a CMC embedding which is very close to one of the embedding of the Clifford family, which is not given by one of these indices here, then it must be congruent to a member of the Clifford family, okay? So that's our result. Observe the minimal value, the minimal radius is never a bifurcation radius for this family, never. Okay, very good. This would be an attempt to reproduce a picture. Of course, here the dimension, the minimal dimension, it would be in S3 would be in dimension 4. So I mean, just this would be the idea of a sequence of CMC tori that converges to like a member of the family, more or less. Okay. Let me tell you what variational bifurcation is. What is bifurcation? You have to have a differentiable manifold, a family of smooth functionals depending on a parameter, a family, well, a curve of critical points. X lambda is a critical point for F lambda for each lambda. That has to be a smooth curve. And the definition is that you have bifurcation of critical points at the instant lambda 0 if there exists a sequence lambda n tending to lambda 0 and xn tending to x lambda 0 with the property that xn is a critical point for the functional f lambda n, but it's not equal to the corresponding member on the curve. So the picture would be more or less the following. These are the lambdas, these are the x's, this is the trivial branch of critical points, and then at some point you have accumulation of other critical points, okay? In the case we look at, we don't really have bifurcation of critical points, but rather bifurcation of critical orbits. Because remember that there's two groups acting. So if you have a Lie group acting on the manifold, and each F lambda is invariant by the action of this group, then whenever you have a critical point, you have a whole orbit of critical points. And then you say that you have orbit bifurcation if you're given a sequence, well, if you're given a sequence of critical orbits that converges, but that they're not equal to any member of the, say, trivial branch, okay? Now, the first observation is that, okay, there's many theorems that give you sufficient conditions for bifurcation, okay? But all these results require a quite involved variational setup. You really need to have a nice manifold, you need to have smooth functionals, you need to have Palais-Smith condition, you need to have a lot of technical properties like friendliness and things like that, okay? And what these results tell you is that usually bifurcation occurs when you have a degenerate critical point where the Morse index of the family jumps. So jump of the Morse index. In the equivariant case, rather than jumps of the Morse index, you must have a jump in the so-called critical groups that I'll tell you in a moment what they are. Okay, I think I probably need to start going a little faster. Okay, so a scheme, if you want to prove the main result, you have to introduce a set of embeddings of M into N, and the question of the choice of regularity is crucial here. You must have a manifold structure on the quotient of the embedding by the diffeomorphisms. Remember, take quotients. You need to have a manifold structure. You need to have the action of the isometry group on this manifold. And then you have to introduce the volume and the area functionals. And then CMC embeddings would be constrained critical points of area with volume. And then the result of accumulation of non-congruent CMC embeddings would be the same as a result of bifurcation for constrained critical G orbits. Okay, very good. So how do we get a result of bifurcation? Okay. There's surprisingly very few results of bifurcation for CMC embeddings in the literature. Actually, I only know one before ours, which is a result by Mazzeo and Packard talking about bifurcation of nodoids in infinite nodoids in the space, in the 3 space. And so there is there's no general theory, and we wanted to formulate a theorem that could be applied to a general situation, not just to the Clifford problem. Okay, so we axiomatize some properties that are needed for our theorem, and what I will do here, I will describe shortly this abstract result for you, and then I will tell you how that fits into the problem we have in mind. So you want to have a smooth manifold modeled. Actually, a Hilbert space would be much better, but we can't do it in the CMC problem, so I have to take a Seprobonic space. You have to have a compact, say, connected Lie group acting continuously on the manifold. I need to have 2 smooth functions. One I call A, you probably guess that comes from area, and one I call V, that comes from volume. They have to be G invariant functions. The volume function has to have no critical point. What you need to have is that the action is not assumed to be smooth, but we need to assume that at least the critical points of the constrained function, I'll say lambda here is a Lagrange multiplier, have to be smooth submanifolds. So continuous action, but the critical points must have a smooth orbit. For instance, in the CMC variational problem, the manifold M would be embeddings modulo diffeomorphisms. X would be some sort of space of sections of some vector bundles over M. G is the isometry group of the target space. A is the area, V is the volume, and lambda is the mean curvature up to some factor, whatever. The thing is that this is not enough. You need to have a strong Hilbert and Fredholm structure in the background. So you have to swallow the next 2 slides full of technical things that have to do with these 2 guys, Hilbert and Fredholm. Okay? You need to axiomatize that the gradient map, the gradient would be, okay, remember you're on a Banach manifold, so the gradient would be a function that goes, let's say, from the Banach space to its dual, whatever. Dual of a Banach space is an ST object. You usually have no Fredholm operators between a Banach space and its dual. Okay, but you really need to have Fredholmness. So you must axiomatize that you must have a Hilbert space in the background that contains that contains your model Banach space in such a way that the derivative of your functionals can be extended, let's say, to a Fredholm map between these two different spaces. Y would be some sort of subspace of the dual, okay? So you must have Fredholm first derivative, whatever that means. And if you have this axiom, then you can prove the local placement condition for the functionals. This is essential for bifurcation. And also you use this to prove that you have a manifold structure of critical orbits near non-degenerate ones. And this is used to prove the stability part of our result. For instance, in the CMC problems, the space X is the space of CK alpha sections of the normal bundle of a given embedding. CK alpha K is greater than or equal to 2. This is the space of maps having K derivative, which is alpha Lipschitz, okay? Alpha, hold it. There's a problem here with this space, I'll tell you in a second. And Y is usually CK minus 2 alpha. H0 is just L2. The Fredholm map is, of course, the classical second order quasi-linear differential equation of elliptic equation. And this is a Fredholm map if you look at it from CK alpha to CK minus 2 alpha. And the derivative of F is the Jacobi operator, which is strongly elliptic. And so by Schroeder's estimates, this gives you Fredholmness, okay? Okay, why did I choose CK alpha? Okay, let me tell you something funny here. So really what you would like to have is a Hilbert manifold structure, okay? So what is the nicest Hilbert space, you know, if you want to deal with this problem? For instance, Sobolev H1. But that's not good because there is really no general theory of regularity for quasi-linear elliptic equation in H1. So that if you use this, you may end up proving bifurcation by something which is not regular. And we don't want that. You don't want to prove bifurcation by something that you don't even know if it's a continuous thing. So this doesn't work. So why not taking Sobolev HK? Because then the Jacobi operator is no longer Fredholm. If you take more than one derivative, the Jacobi operator is not Fredholm. So no way to have a Hilbert space structure. You have to go to Banach manifolds. C infinity, no way. This is no Banach. This is Fréchet, of course. So no theory, no C infinity theory. I'm sorry for you geometers. I know geometers don't like anything which is not C infinity, but there's really no way. What about CK? CK doesn't work because the J is not Fredholm in CK. It is Fredholm in CK alpha. But you know what? CK alpha is almost fine, but this is not a separable space. I mean, it's really weird, but if you take C0 alpha, for instance, you take the function x minus a to the power alpha and x minus b to the power alpha with a different from b. These are nice C0 alpha functions. And if you compute the distance of these two objects in the metric of C0 alpha, you'll find that this is greater than or equal to 2 for any pairs A and B. So you have an uncountable family of elements that have the same distance. That means that the space is non-separable. Yeah, we almost gave up when we got to this point because this is really weird and you need separability in a lot of issues. But there's a way of handling this problem is rather than CK alpha, you have to take a proper closed subspace of this CK alpha. I don't want to get into details, but basically it's the closure in CK alpha of CK or C infinity functions, and that is separable now. So, okay, sort of technical problems. This is another somewhat nasty slide, but we have to go through that. You also need some other kind of Fredholmness that we couldn't relate to the first notion of Fredholmness. You need to have basically that the second derivative is represented by an essentially positive operator. Essentially positive means that the essential spectrum is positive. And this is used for two reasons. One is to compute the Morse index, which is the sum of the dimensions of this operator, and also to use Morse theory, because we want to use the Morse lemma, and Morse lemma needs Fredholm second derivative, so you need this. And I tried very hard to figure out what picture I could put here to visualize this situation. And the only thing I could come up is with a picture of Hilbert and a picture of Fredholm. That's the best I could do, I'm sorry. So how does this become for the CMC problem? H1 is the space of H1 sections of the normal bundle. And the second operator is this quadratic form, which is product of the gradients, and then Ricci curvature and second fundamental form. Now, this part here is an inner product of H1, so it's a positive isomorphism of H1. It's represented by a positive isomorphism. This part here doesn't involve derivatives of V1 and V2, so that means that it's represented in H1 by a compact operator. So you take positive plus compact, that's essentially positive, and that finishes the problem. So the theorem we managed to prove is that if you have all these axioms satisfied, A1 to A5, and then these Hilbert-Fredholm axioms, A and B, if you're given a smooth map of Lagrange multipliers, a smooth map of constrained critical points, assume that, you know that there's group acting, so assume that the stabilizer of each critical point doesn't depend on R, and assume that for all R's, the critical orbits of this family are non-degenerate. They only degenerate at the instant R. And suppose that you have at this R bar, and suppose that at this instant R bar you have jump of the Morse index, then you have critical orbit bifurcation. So that is the theorem that we apply to get our result. Okay, so let me discuss with you this variational problem now. Which are the functions A, what is V? Okay, take a compact manifold and a Riemannian manifold of codimension 1, okay? Take an embedding, take the pullback metric, and you call vol star the volume of this pullback metric. Then the area of X would be the integral of this pullback volume, okay? Now, what is the volume and embedding? Now, this is a picture. This is the egg represents N, and this circle represents now the image of M. When the image of M is the boundary of an open set in N, then you can define the volume to be just the volume of this open set, okay? But that's not always the case, that the image of a compact manifold bounds an open set, right? So how do you define a volume if you don't have this? Okay, when is it that the image of an embedding is a boundary of an open set? That depends on the number of connected components of the complement set, right? If there are two, then it's fine. If there's only one, then we have a problem, right? So this is given by the rank of this reduced homology group of the H0 tilde of n minus m0. So you want to study the rank of this space, so you have to use the long exact reduced homology sequence. Gives you this. You do an easy analysis of this object, and you find out that this is 0 or 1, depending on the fact that this map that you see here, that one that sends the first homology group of n into the first relative homology group n minus image of m, this has to be, if it's 0, then we have two connected components. If it's 1, we only have one connected component. That is the proposition. So you can study this via homology. The picture is more or less like this. Suppose that the manifold, the ambient manifold is a torus, and the source manifold is a circle. If you embed it in a way which is homologically non-trivial, then this is not the boundary of anything. But if you embed it in a way which is homological trivial, of course it's a boundary or something. So that's what you have to look at. So what do you do when the homological triviality property is not satisfied? Then you invent a generalized volume function, which works more or less in the following way. Suppose to start with that n is a non-compact manifold. Then the volume form is exact, right? So what you can do, you call eta a primitive of the volume form, and you define the volume of X to be the integral of the pullback of eta, okay? Notice that if this definition generalizes the one we had before by Stokes' theorem, because if in fact X of M is the boundary of omega, then an easy computation that uses Stokes' theorem that tells you that the volume of X is really the volume of omega, okay? So if the ambient is non-compact, you don't need to worry. You have this definition. But if it's non-compact, then what you do is you take a compact manifold, take a point which is not in the image. The image of a differentiable manifold cannot be the entire manifold because of Sard's theorem, right? So you take a point, remove it, and no more compact. And you define this volume function just by removing a point. That is only, well, of course, that will depend on the point you remove, but it's okay. No problem. You can do that. And bifurcation is a local problem. So. Okay. I would like now switch to the study of the manifold, of embedding modulo diffeomorphisms. That took us quite some time to understand this, to understand the manifold structure of this. The idea is that up to diffeomorphisms, you can describe nearby embedding. You're given a smooth embedding X, and the nearby embeddings are actually given by exponentials of sections of the normal bundle, small sections. So if you have a smooth embedding, take the normal bundle, take a nearby embedding, there exists a unique section of the normal bundle such that y is the exponential of this, okay? So you have a bijection. Nearby embeddings with small sections of the normal bundle. So you have local charts, right, for your manifold of embedding. Yeah, this is a local chart for this quotient, okay? And that takes value in the space of sections of the normal bundle. The thing is that two charts like that are not differentiably compatible. That's something really, really weird, and that depends on the fact that we don't consider only C-infinity embeddings. That was early. I mean, we studied very deeply this problem, and I think this is probably one of the most interesting thing we have found, that this object here, in fact, doesn't have a natural manifold structure. That is. But the thing is that we're safe, because if you take a map on, oh, there's a target mid. If you take a smooth map taking values in R, from the space of embeddings itself is fine. This is an open subset of a Banach space, so this is fine. The problem is the quotient, of course. But if you take a smooth map which is invariant by diffeomorphism, then F composed with any of these chart gives you, in fact, a smooth map. So that takes care. Let me see if, okay, maybe I can go quickly on this. Why isn't that a manifold? There's a problem with differentiability of the composition functions. Let me give you this example. Take F, capital F, to be a map between these two manifolds, B and C, and consider the operator of composing on the left with this capital F, right? Now, this function here is not differentiable. The composition on the left map is not a differentiable map, and that depends on the fact that the differential of the composition on the left is the composition on the left with the differential, okay? But the differential lowers the regularity. You see, if F is only of class CK, the differential of F is of class CK minus 1, so that this operator is not even well defined in the correct space. Okay? So the composition map is not differentiable. And for the same reason, also the inverse map. If you take the group of diffeomorphisms of class CK with k less than infinity, this is not a Lie group. The composition, the inverse map is not differentiable. And this has to do with the problem we have in mind, because when you take transition maps between two normal sections in this sort, I'll go quick on that, I'm sorry. What you need to do is you have to take composition. If you want to take a transition map, this is a composition on the left, basically, by two exponentials. And what you get is not another section. It's something that needs an adjustment, and now you have to compose it on the right, and that sort of screws up the differentiability of the property. So the theorem is that this object here doesn't have any natural differentiable structure. That is, natural, I mean that the quotient map has to be a surjection, so there is no way you can do it. And for the same reason, the action of G is only continuous, but the orbit, or the G orbit of smooth embeddings is smooth in local charts, and that's because now you don't have the problem. When everything is C infinity, there's no problem. It's only when you have something CK in the middle, and so that's the thing. Okay. So to finish basically the proof of our result, we have to study what is the stabilizer of a Clifford torus. That is the only object that was left. So what is the stabilizer of a Clifford torus? The image of a Clifford torus is, of course, the product of these two spheres, right? And the product of AOJ plus 1 times OM minus J plus 1 is clearly contained in the stabilizer of this, but it may not be equal. For instance, when J equals M minus J, and when R is equal to 1 over square root of 2, you also have other elements in the stabilizers. For instance, the flip map, which is not one of these. But the thing is that the connected component of the stabilizer is this. And that is because this object is a maximal connected subgroup of SOM plus 2, which is the isometry group. So you can't have anything bigger than this. So the connected component of the stabilizer is always this one. And you see that this doesn't depend on R. And so that, okay, this is the stabilizer, which means that you can compute the dimension of an orbit, which is given by dimension of the entire group. Of course, this acts transitively. So dimension of the bigger group minus the dimension of the stabilizer, which is this. You do the computation, you get this number, and you probably recall that we had computed the multiplicity of a 0 for the Jacobi operator, which is exactly the dimension of the stabilizer. That means that, that all the orbits are non-degenerate, except for those belonging to the sequence I am talking about. So non-degenerate critical orbits. Oh, okay. No, there was something else. There was local homological invariance. Let me see if I can go quickly. I told you that I have to, I really don't have to look at jumps of the Morse index, but rather at jumps of the critical groups. What are the critical groups? These are homology groups that you can compute this way. Take a critical point. C is the value of the function of the critical point. Take its critical orbits. Take the C closed sublevel of the function that contains the critical orbit. The kth critical group is the kth relative homology space of the entire sublevel. I have to do it this way. Modulo entire sublevel minus orbit. F is just any coefficient field. Okay? Now, we proved that if you have non-degenerate orbits, take the Morse index, use the axioms that we had. We can compute this object. These are just, okay, the kth critical group. Well, the critical groups correspond to the homology of the orbit, actually, but just shifted by the Morse index. In particular, you see, the orbit is always the same, doesn't depend on R. And so the homology also, the orbit is always the same. But there's a shift here. So jumps of the Morse index are exactly jumps of the critical groups. So in this case, jumps of the Morse index is the same as jumps of the critical groups. I had a proof of this. I won't show this to you. Okay. So this basically concludes the proof of my main result. There's a few more questions that we're currently working on and that I would like to mention here, which are the following. What about establishing what kind of bifurcating branch do we get? Is this a continuous branch or a smooth branch? Usually, you have lots of results that give you like smoothness of bifurcating branch, but they cannot be applied directly here because exactly of this lack of smoothness property. So we have to use non-smooth bifurcation results that don't actually give you smoothness of the bifurcating branch. Although it is, of course, very likely that you get a nice smooth branch of bifurcating objects near the ones, but we don't have a proof of that. Something that we want to study is whether bifurcation also gives break of symmetry. That is, the Clifford tori are extremely symmetric. They're the most symmetric thing, CMC embeddings that you can possibly find. So clearly, the bifurcating branch consists of embeddings that are not that symmetric, right? So we want to study exactly what kind of symmetry do this bifurcating branch have. Like, this is a very interesting problem. Then let me mention that there's also a joint project which is starting right now, which is to study bifurcation also in symmetry breaking for CMC Clifford tori, but now in Berger spheres. This is something which is due, the construction of this family of symmetric CMC embeddings is due to my friend Levy. And this is a project that we have with George and Levy. And I told you I would show you pictures of my advisors. This is the place where we, no, I'm sorry, I made a mistake here. I need to use this. This is the place where we discussed this problem. Yeah. This is Levy and George. We didn't go very far on this, but and finally, I think I probably have 5 more minutes. I want to tell you another problem that I've studied. This is a bifurcation problem for CMC embeddings, but now with boundary and with fixed boundary. And this is a problem that I'm studying with Miyuki, Koiso, and Bennett Palmer. Let me show you a picture. This is Miyuki, and this is Bennett. And this is this is the following problem. You fix 2 parallel planes, pi1 and pi2 in R3. You take 2 circles with the same radius and with centers aligned on the orthogonal line. And in this case, there exists a 1-parameter family of nodoids, NT, that intercept those 2 planes exactly at these 2 circles. There's a 1-parameter family of nodoids. Okay, a nodoid is a rotationally symmetric CMC embedding into R3, which is given by something. It's not an embedding. I'm sorry. It's an immersion. It's something of this type. So there is a 1-parameter family of nodoids, and at a discrete set of values of the parameter, so there's a sequence tk that goes to infinity, this nodoid becomes tangent to the two planes, okay? So in general, this one parameter family, it's like nodoids flatten up, and at some point they become tangent, right? Now, the result we have is that when they become tangent, then there is bifurcation there. There's bifurcation by other CMC surfaces that pass through the same, that have exactly the same boundary, but they're not, okay, this bifurcating branch breaks symmetry, like they're no longer rotationally symmetric. We can prove this in this case. Break symmetry, we can prove in this case. And also we studied a similar problem for a more general variational problem like this anisotropic CMC. It's a similar variation problem. The proof of this is that you have to study, in this case the variational setup is much easier. When the ambient space is a vector space, then everything becomes easier. And so actually you only need an analysis of the Jacobi operator in this case. And if you take like the normal field of the embedding of the, maybe I can draw a little picture. So it's like you have a rotation of something of this type. You take the normal field of the embedding and you decompose it into its three components, nu1, nu2, and nu3. Then nu1 and nu2, well actually also nu3, but nu1 and nu3 are Jacobi fields in this case, because they correspond to translation of the space in the direction E1 and E2. And of course, translation preserves anything. The thing is that these Jacobi fields in general do not satisfy the correct boundary conditions, right? Because they may not be zero on the boundary. And they are zero exactly, of course, when, so when you have here tangency, then the normal vector would be like that. So it has zero components over this side. So at the instant when the nodoid is tangent, then you have true Jacobi fields for the problem. And we analyze the situation in this case, and we see that in fact these zeros in the spectrum of the Jacobi operator corresponds in fact to a jump of the Morse index in this case. So we do have bifurcation. How do we know that the bifurcating branch in this case consists of non-rotationally symmetric objects? Because the only rotationally symmetric solutions of the problem are nodoids. And what we find are not nodoids. So only discrete group of symmetries. That's the same. This is my last slide. I want to give you the essential bibliography of what I've talked about. This first paper is the paper where we took the computation of the spectrum of the Jacobi operator for the Clifford tori, Luis Alias, Aldir Brazil, and Oscar Perdomo. This is the preprint that contains what I discussed today with you. This is a paper that appeared a couple of years ago on the archive, where supposedly it's proven that every CMC embedding of the torus in S3 is rotationally symmetric. If that is true, that would be a proof of the Lawson conjecture. And this is the only paper that I know that talks about bifurcation for CMC embeddings. It's by Mazzeo and Packard. In their case, the analysis, the variational analysis is much easier, but the problem is studying the spectrum of the operator is exactly studying zeros of the Jacobi operator. I was helped very much by my student Renato for making these pictures, and I want to show you his picture. For who doesn't know him, this is him. And I think this is my last slide. So thank you very much for your attention. Any question? How do you know that the unknown?